Okay, in our problem set, let's take a look at problem number 11 here, doing some radioactive decays. An alpha particle emitted when this particular nucleus disintegrates. So first of all, this is the chemical symbol W. Does anyone know what that is? If I want to look at a periodic table, this is actually tungsten. Yeah, the German name for tungsten is Wolfram, which starts with a W, so that's where the W comes from. So this is tungsten 184. And first thing we do is write a full nuclear reaction, including the electrons. That's a little bit different, but let's tell you what's going on with this. So first we're going to start by writing tungsten 184, and of course, if it's a neutral atom, it comes with 74 electrons. We write it like so. It's going to decay from an alpha particle, which means we know one of the particles is going to be the helium nucleus, helium-4, and it's associated with 2 electrons, because it's got atomic number of 2. And now we have to predict what the daughter is going to be. So why don't you pause the video, figure out what the new nucleus is going to be. So we're going with our conservation laws. We have the conservation of mass numbers on top, and conservation of atomic number or charge, that's the number on the bottom. We should be getting hafnium, right? 184 splits up into 4 and 180. 74 splits up into 2 and 72. Any element, any atom, I should say, with 72 protons has to be hafnium. You look at your periodic table. I don't expect you to know these ones. You look these up on the periodic table. And since we're including electrons, hafnium comes with 72 protons, comes along with 72 electrons. Okay, so why am I talking about this whole deal with including the electrons? Well, we look at our appendix. Maybe you have to look at the appendix to find these things. But if you didn't, here it is, the appendix. Here is tungsten, and here is hafnium. We'll be using these values here for atomic mass. And it turns out that these numbers, everything in this column, actually already includes any associated electrons that comes along with it. So when we look for the masses here, it already has electrons included, which means that really when you find the mass of the tungsten nucleus, it already includes 74 electrons, the helium already includes the 2 electrons, the hafnium already includes the 72 electrons. So it's kind of right to write the electrons. Now here, obviously, if we have 74 electrons, we have a 2 and 72, we have a total of 74 electrons in the end, so there's nothing weird happening here. So you don't actually have to write them, but it's good to show that these numbers are already included. All right, letter B, you want to find the mass defect. Remember, that's the difference in mass, the discrepancy in mass. We're really just finding delta M, the change in mass from beginning to end. And so in this case, it's going to be the mass that we start with. I know it's sort of in reverse, but I want to find a positive number for delta M. Although, yes, a loss of mass means something. Just it makes a little more sense to just find the mass defect, right, instead of a negative mass defect. So we're going to say we'll do larger minus smaller. And since we know it's a radioactive decay, we know it's an unstable nucleus, we know it's radiating alpha particle because it was unstable, it's going to lose mass. This is going to be the larger value. So it's the mass of the original nucleus minus the mass of anything afterwards. Now, this is going to look a little bit different from how we're used to doing it. We're used to finding the masses of all the protons and neutrons that combine to make a nucleus. That's not this type of problem. In this nuclear reaction problem, we're just telling out the masses. We already know what the particles are. We're not forming nuclei. This already is a tungsten nucleus. This is going to be a hafnium nucleus. This is going to be a helium nucleus. We're not combining the constituent nucleons to make it. This is a different type of problem. So this is different, right? We're just going to look up the masses of these nuclei and find them on the appendix table. And make sure we're finding the right isotope, right? This is going to be tungsten 184. This is going to be hafnium 180. This is going to be helium 4. And it's all right here, and you're going to look in your appendix. So this slide's only going to be up on the screen for a little bit. All right, so here's helium 4. Make sure we're looking for the isotope as mass number 4, this one. Hafnium 180 and tungsten 184. So make sure we're using those values. So go ahead and you write down what the values are. Okay, don't just copy what I have here. Make sure you've done this, right? So try it on your own. Make sure you're getting the same ones. This should be the tungsten 184. This should be the helium 4. This should be the hafnium 180. Now again, make sure we're not just writing down the mass numbers. We're going to get a delta M of 0. That's not the point. Remember, the mass number is just telling you how many things are in the nucleus. That's not the actual mass. The only way to find the mass is to look at that table. Look up these numbers. Okay, so now just carefully type it all in your calculator and get the mass defect. There it is, 0.001781. We always want to be careful with our units in this topic. It does say specifically put it in atomic mass units, although if it didn't say that, we certainly could have expressed it in kilograms, and sometimes it might be useful to put it in kilograms. We just have to do a unit conversion with our conversion factor between atomic mass units and kilograms. Let's go on to problem 12. Okay, this time it's thallium-210, and decay by emission of a beta particle. Now we know there's two different types of beta decay, beta positive, beta negative. Beta negative was the first one that was discovered. So it's always assumed, if you just know it's a beta decay, we're assuming it's beta negative. We're going to assume it's the electron one. If they want you to tell you that it's a beta positive, they would actually go out of their way and say beta positive. Okay, so why don't you go ahead and try writing the full nuclear reaction on your own. Of course, you have to know what thallium is, and you just look on your periodic table or find an appendix. It's going to be symbol TL. Okay, so it should look like this. So it's element number 81. Here's thallium-210, and it's 81 electrons. If it, again, a beta particle is just an electron, and then by conservation of mass number, 210 is still going to be 210. 81 with a negative 1 here has to go to 82. So here it goes 1 to the right on the periodic table to element number 82, which is lead. And lead comes along with the 82 electrons. One of them is already here, coming off as the beta particle. Here's the remaining 81 for a total of 82 electrons to balance out the 82 protons. And remember, a beta decay comes along with the anti-neutrino. So this is not a complete and correct equation until we have the anti-neutrino there. So this is what the reaction should look like, including the electrons. And then if we were to do anything with the masses, remember that if we look up the thallium nucleus mass, it already includes the 81 electrons, and the lead nucleus mass already includes the 82 electrons. But that's something's a little bit weird here, because the second question asks, where does this beta particle come from, right? We start with 81 electrons, we end up with 82 electrons. Where is this beta particle coming from? Why don't you pause the video, take a couple minutes, and really think this one through. So don't just unpause the video and listen. Really, I want you to really think it through and see if you can figure out where the beta particle is coming from. All right, I know from experience some students say, oh, it's got to be the exchange of energy, right? The energy is absorbed to form the mass of the beta particle. That's a great guess. That is not it. If you're still stuck, it's in the numbers. Look at the numbers on the left-hand side and the numbers on the right-hand side. You can do this. Pause the video again, see if you can figure it out. Do you see it? Look at the charges. Look at the number of protons, right? It starts with 81 protons. That also changes to 82. But look at the mass number. The mass number hasn't changed. How could this be? How could we still have the same number of things in the nucleus, but we somehow gained an extra proton? What does that mean? If there's still the same number of things in the nucleus, but there's one more proton, what did we lose? A neutron, right? What happened to that neutron? A neutron actually decays into a proton electron. That's the only way it works. That's crazy, right? That's what actually happens. One of the things in the nucleus, one of these 210 things, one of these neutrons splits up to form the new proton and this extra electron. If we write this as a reaction, it would look like this. One neutron inside the thallium nucleus splits apart into a proton and electron. Look at all the numbers. Everything balances out. This is the process for beta decay. A neutron inside the original nucleus, the parent nucleus, actually splits apart into a proton, ends up in the daughter nucleus, and this beta particle, this electron, which goes zipping away.